So we have a sinusoidal electromagnetic wave, as we were just discussing. And the wave is propagating the positive x direction. Okay, we're choosing that to be the direction that the wave is moving in. And there is an electric field and a magnetic field present. And what I want you to notice about the electric and magnetic field is, okay, I've put the electric field along the positive or possibly the negative y-axis. Okay, so E is along the y direction, B is along the z direction. Well, what you call x, y, and z is completely arbitrary, okay, how you choose to orient these axes. The important thing, though, the thing that is a physical law when it comes to electromagnetic waves, is that the direction of the electric field is perpendicular to the direction of the magnetic field at any point in which the wave is propagating past. And the electric and magnetic fields are both perpendicular to the direction the wave is moving, in this case, in the positive x direction. That's something that I want you to remember. Electric field is perpendicular to the magnetic field, and both of them are perpendicular to the direction of the wave motion when you have an electromagnetic wave. That is always true. And you'll notice the electric and magnetic fields are in phase with each other. So if there's a wavelength characterizing the electric field, it's exactly the same wavelength characterizing the magnetic field. And where you have a maximum electric field in one direction, you'll have a maximum magnetic field in one direction. And where you have the electric field pointing maximally in the opposite direction, in this case minus y, you'll have a magnetic field pointing maximally in that direction. In other words, all I'm saying is the peaks and the troughs of the electric field and the magnetic field parts of the waves are at the same positions. Okay? Where the electric field is 0, the magnetic field is also equal to 0. That's this point, and this point, and this point. Okay, so there's what an electromagnetic wave looks like for a single line of points along the positive x direction. Now, what we're trying to illustrate here, and this is kind of hard to visualize, hard to understand, but we're trying to describe something called a plane wave. Now, a plane wave, to understand a plane wave, you have to refer down to this bottom picture here. And so you have this kind of square cross-sectional tube, it looks like. Well, it's just a region of space that we're considering here. And if you take in this box-like, imaginary box-like structure, it's not a real box, it's just a volume, okay, arbitrary volume, oriented along the positive x direction, that's the direction in which the wave is moving. If you take a cross-section of this box, all points in this plane, for example, right, the end of this box, every single point in that plane, the electric field will be in phase with the electric field at every other point in that plane. The magnetic field will also be in phase with the magnetic field at every other point in that plane. Again, this is something that's a little bit hard to understand, hard to visualize, I should say. Not too difficult to understand, but you really have to try to think in 3 dimensions. So what I'm going to do, I'm going to leave this as an exercise for you to read the textbook, see what the textbook has to say about plane waves. Okay? And try to understand what it says about plane waves. But what I really want you to understand is this picture here. Okay, this is, yes, it's a picture that's relevant for plane waves, but it says some really important things. That is, it gives some of the really important properties of electromagnetic waves. Okay, so an electromagnetic wave is an oscillating electric and magnetic field. Okay, and the relationship, well, there is a relationship between the electric and magnetic field. We've seen what one of the relationships is. The electric field is perpendicular to the magnetic field, and both are perpendicular to the direction of the wave motion. There are other properties of the electric and magnetic fields that we don't have time to discuss in this course. You can read about it in the textbook if you're curious. Another thing to note is this wave is describing what we call a monochromatic wave. A monochromatic wave. Literally that means one color or one wavelength. So for electromagnetic waves, if it's visible light, the wavelength tells you what the color of the light is. So if you increase the wavelength, then you'll maybe see a more reddish color. For somewhat smaller wavelengths, you'll see maybe a bluer color or a violet color. Okay, that's the visible spectrum of the electromagnetic spectrum, or the visible portion of the electromagnetic spectrum. Okay, so again, wavelength goes with color if it's in the visible range. That's another thing that's useful to remember. Now, real light most of the time is a mixture of many different colors, therefore a mixture of many different waves of many different wavelengths and frequencies. So a mixture of wavelengths, a mixture of colors, the wave would look much more complicated than this. This is what a wave would look like if you were to illustrate the electric and magnetic field vectors. This is what the wave would look like for a single color. Okay, we're almost done here. A couple more equations. Probably we're not going to use these equations in this course, but we've already referred to this equation. Well, I can't quite highlight it. There it is. What is it? It's the energy density associated with an electric field. Now, we don't have time to derive the second equation, but it's basically the same kind of equation. It's saying that there's energy stored in a magnetic field as well. And as was the case for the electric field, the energy stored in a magnetic field is proportional to the square of the magnitude of the field. The proportionality constant is different. We have mu naught appearing in the denominator here, whereas we had epsilon naught appearing in the numerator up here, or just, not appearing as in the denominator. We're multiplying by epsilon naught, dividing by mu naught is what I'm saying. Don't worry about that. That's not the important thing. The important thing is both are proportional to the square of the magnitudes of the fields. What is an electromagnetic wave? What did we just say it was? Well, it's complicated, but what we've seen is it's an oscillating electric and an oscillating magnetic field. And electric and magnetic fields both store energy as electromagnetic waves propagate through space. And this can be through completely empty space, like the space between the sun and the earth is mostly empty. Light goes from the sun to the earth, fortunately. Energy is transported with that wave, with the electromagnetic waves from the sun to the earth. Okay, and this is telling you something about the energy stored in an electromagnetic wave. We're not actually going to use these equations to do any problems with. We don't have time, but I just want to make that point. Electric and magnetic fields store energy. Energy, therefore, gets carried with an electromagnetic wave. Finally, one more thing which turns out to be really interesting. These two constants here. Epsilon naught was a constant that was related to the Coulomb constant. Go back in the notes and you'll see it's related to the constant K in Coulomb's law. Mu naught is a constant which is relevant for magnetism. And I've given you the values of both of these constants. You can do experiments to measure what these constants are. Experiments with electric fields to measure epsilon naught. Experiments with magnetic fields to measure mu naught. Now the really interesting thing is these equations that I referred to earlier, which I haven't shown you, but which are in, I think, chapter 29 of the textbook. These equations called Maxwell's equations, which tell you all the properties of electric and magnetic fields. They predict that first of all, that electromagnetic waves exist, and secondly, that the waves travel with a speed, we call it c, the speed of light, which is related to both of these two constants. It's 1 over the square root of the product of the two constants. And if you calculate this quantity, you'll see that it's exactly, well, not exactly, but close to 3 times 10 to the 8 meters per second.